So today we're going to be looking at the Edexcel level 3 GCE. So this is our A-level paper. Paper 2, we've already done paper 1 apparently. I think that might have been during the subathon or at some point in the last like 3 years since I downloaded this. But yeah, so I thought we could have a look at some further pure 2 maths. So this should be, in theory, in the wheelhouse without too much stress or prep. We'll see whether or not I eat my words. So this would take 2 hours. I've got a feeling we're not going to get through everything, even though it will take us 2 hours. Okay, we've got the formula book. We've got mark scheme if we need it. Let's do this. So kicking things off, we have a function, x cubed plus 2x squared minus 8x plus 5. Find f double prime x. So this is equivalent to the second order derivative, which we can find by finding the first order derivative and then taking the derivative of that one. So if we have f of x is x cubed plus 2x squared minus 8x plus 5. To take the derivative of this, we have f prime of x. So the derivative of ax to the n, actually, let me do that in a different color. So when we take the derivative of this, so the d dx, there's like a long form way we can do it, but basically the trick is that you leave the coefficient at the front alone. So you leave the coefficient at the front out alone, and then you take the power and you bring it down. So we now multiply by the power that it was, and then we take one off the power. So x squared goes to 2x. So we bring the 2 down and we take it off. So here we have x cubed, so that becomes 3x squared. Plus we have 2, and then x squared goes to 2x. So 2 times 2x. X to the 1 goes to 0. So x to the 0 is 1, so 8. And then the plus 5 doesn't have any powers of x in it. So when we get rid of when we differentiate that, it disappears entirely. So here, whoops, forgot to switch back. F prime of x is 3x squared plus, write it out this way, 3x squared plus 2 times 2, so 4x minus 8. And then we do the same thing again to get f double prime. So we take the 2 here down, and that gives us, so 3 times 2, x plus 4. And then the minus 8 has no x's, so that just goes away. So f double prime of x is 6x plus 4. Okay. Then we need to find, okay, part B. So if I label that part A as well. So part B is solve f double prime of x equals to 0. So that's just plugging in our values. So we have 6x plus 4 equals to 0. So solving this, we get 6x, and we're going to take the plus 4 over, and that gives us minus 4. So you basically, like, how do we get rid of it on one side? We do the same operation on both sides. And then we need to just get x on its own. So we divide through by 6, so minus 4 over 6. So 4 and 6 do have a common factor, right? They're both divisible by 2. So that means that we can divide through top and bottom by 2, and we get x is minus 2 over 3. There was a second part of that question. Hence, find the ranges of values of for x for which x is concave. A function is convex when, if you take a point and another point further down the line, the chord that joins them, does it sit above or below, basically. So this one would be convex, whereas here you take a point and a point past it, and you connect the two, and it sits below, concave. And if it's above, like if it's a straight line graph, then it depends on, it's sort of both at the same time. So we're looking for a concave function. So we're looking for when the rate of change is decreasing. So concave f double dash of x is less than 0. So luckily we have what f of double prime of x is. So we have 6x plus 4 is less than 0. So f of x is concave when x is less than minus 2 over 3. Because we solved for equal to 0 here. So now we have less than 0 for minus 2 over 3. So that was 4 marks. 4 marks for question 1. I think that's everything on that one. I give you a lot of space for it. Okay, question 2. Sequence U1, U2, U3 is defined by these expressions. So we start off with U1 is 35, and then everyone after that is the next value is, if I do it this way, does it still do it? Yeah. Okay, so UN plus 1 is UN plus this expression. Here, U1, so this would be 35, and then U2 would be 35 plus 7 cos, so n in this case is 1, so pi over 2 minus 5 to the minus 1 to the power of 1. And then number 2 would be whatever that thing is plus, and then it would be 2n minus 5 to the 5 times minus 1 to the power of 2, and so on. So show that U2 is 40. So U2 using this expression that we're given is, as I say, 35 plus 7 cos 1 times pi over 2 minus 5 to the minus 1 to the power of n, which in this case is 1. So this is going to be equals to, so 35 plus, so cos of pi over 2 is something that we probably should know, but I've forgotten it, is 0. So minus 1 to the power of 1 is minus 1, so that minus 1 stays as it is. So that's 35 plus 5, so U2 is 40. Part 2 of this question then is find the value of U3 and the value of U4. So U3 is going to be U2 plus 7 cos 2 pi over 2 minus 5 minus 1 to the 2, which if we plug in, we get 40 plus, so cos of I is minus 1. So we get 7 times minus 1. And now the minus 1 is now squared. So it becomes plus 1, so we leave the minus 5 alone. So this is 40 minus 7 minus 5 is 28. And U4 is going to be, so now this is going to be U3 plus 7 cos 3 pi over 2 minus 5 to the minus 1 to the 3, which is 28 plus 7 times by cos of 3 pi over 2, which is going to be 0 again, minus 5, minus 1 to the 3 is minus 1, so we can leave that alone. Uses a calculator for exacting trig numbers. I said I'd forgotten them. I said we should know what they are, and I've already forgotten them. So it's been a while. 28 plus 7 times 0 is 0, minus 5, so that's plus 5, is 33. Okay. So we have U3 is 28, U4 is 33, U2 is 40, and U1 was 35. Given that the sequence is periodic with order 4, write down the value of U5 and find the value of the sum from R is 1 to 25 of UR. So, part B. So it's periodic order 4, which means every fourth one repeats. So that's U r is the same as ur plus 4 for all values of r. So part u5 should be the same as u1 because it's u1 plus 4, so it's the same. Then this is going to be 35. Part 2 then. If it helps, cos is just the x value of the point on the unit circle at that angle. Ah, yeah. And then sine is the y value. So for a circle, your coordinates are cos of x and sine of x. So what we were saying was with like pi over 2 is like when it's up at 90 degrees, pi is the full way around, and then 2 pi is coming back to the start. So yeah, just thinking about your x coordinate is a really good way to do it. That is really true. Very helpful. Okay. What was it? It was find r equals 1 to 25 of ur. Okay. So what we actually have here is the sum. We've been told that it's periodic, right? So if we find r equals 1 to 4, it would be repeated. So if it was sum over all the values from 1 to 4, it would just be adding those up. If it'd be 1 to 8, it would be adding them up twice. So how many do we need to get to? Well, we need to get to 24. So that's 6 times 6 lots of it. And then that would take us to r is 24. And then we just need u of 25 left over. Okay, so what I'm doing there is because this repeats, I can just multiply, find out what the sum is, and then multiply it 6 times. So 1 in 25 ur is the same as 6 lots of r is 1 to 4 ur, but we need to add in u25 again. So what is this? This is 6 times ur, so u1 plus u2 plus u3 plus u4 plus u25, which is 6. So that was 35, 40, 28, and 33, I believe. Plus, okay, so u25 is 1 after u4. So it's going to repeat. It's going to be the same as u1. So it's going to be plus 35. So this should be 6, and I can plug this directly into the calculator. 35 plus 40 plus 28 plus 33 plus 35, 851. Okay. Question 3. So we've got logs. So we're going to need some log laws would be my guess. And we've got given this, we need to show some stuff. So things that would be useful to know to start with. So a log x is the same as log of x to the a. Log of xy is the same as log of x plus log of y. I'm doing that thing where I write over my name, I'm sorry. There we go. Log of, or is it the other way around? I've forgotten my log laws. Yeah, no, I am right. x over y is log x minus log y. Okay, they may come in useful. We'll find out. Generally speaking, when doing questions, or when doing any sort of problem, it is always nice to sort of write down the useful, relevant stuff just in case you need it. So given that expression, show that this expression is equal to 0. So the first thing that I'm going to want to do is sort of move some stuff around. So let's write it out here. And we're in log base 2, which shouldn't make too much of a difference to us, but we just need to be careful of that when we sort of take the exponent, we're putting it up, like 2 to the power of something. So log 2 of x plus 10 equals 2 plus 2 log 2x. Okay, so I can use the first log law over here to give me a power in my bracket. So I can get log 2 x plus 3 is log 2 x plus 10 is 2 plus log 2 x squared. Okay, well, I've got an x squared term, so that's good. Bring everything over to the same side. Okay, and now we have log of something plus log of something minus log of something else. So we can bring all that inside of one big bracket. So summing them would give me x plus 3 times by x plus 10. And then I'd be dividing by x squared. So that's come from the fact that we've got the pluses. I could do it in stages. I'd have x plus 3 times x plus 10, but then I'd still have log of all of that minus the other one. So we just divide through. So I've just done it a bit quicker, is 2. So now we need to take exponent, but because we have this 2 here, when we take exponent, instead of it being e on the bottom, it's going to be 2, because so normally you've got log x would go sort of inverse to e to the x as sort of reverse operation of each other. But with log of a base of a number, the log base a, that's going to swap with a to the x. Those two functions are the opposites of each other now. So because we're log 2, we're going to take everything, or take the power of 2 or something. And what I mean by these arrows is that e log x is equals to x. And here, 2 to the power of log 2 of x is equals to x. And similarly, log base 2 of 2 to the power of x. They're sort of like, they undo each other. So go forwards, go backwards, and they cancel out. So back over here, we have x plus 3, x plus 10. So because we sort of undo that log 2, x squared is 2 to the power of 2. Now, it's the same thing both ways, but like this 2 is that 2, and that 2 is that 2. Just to make it... I feel like they've done that to be nice, because it would be tricky to catch people out otherwise. So what have we got? We've got x plus 3, x plus 10. I'm going to multiply up by the x squared, and I've got 2 squared, which is 4, x squared. And then we're trying to get to like the expanded expression. So let's multiply this out. So we get x squared from taking these two terms. I always like first outside, inside last as an approach. Stop it. Sorry, I keep leaning on the bottom of the page and then it catches me out. Enjoying listening to this even. If there's any point where like asking questions, like I'm happy to go on a tangent. But equally, if you do enjoy just like listening to me babble, that is more than fine. But I'm glad you enjoy hanging about. It's good. It's been a while since I've done any like just actual sit down and do some maths, so I'm enjoying. Okay, so first outside, inside, last is multiplying through the brackets and taking the first term in each brackets, multiplying them together, taking the outside ones, so we've got x times 10, so 10x, taking the inside ones, 3x, and then last is multiplying those two together, so 30. And then you can check it's done, so everything is multiplied through. Okay, final thing to do is check where we're trying to get to. So we're trying to get to positive 3x squared. Okay, so what is useful then here is we could bring the plus 4x over to the left-hand side, and that would give us minus 3x squared because we'd have positive 1 minus 4. But instead, I'm going to bring everything back over to the other side. So I'm going to take all of this over to that side. So that's going to give me 0 equals to 4x squared minus x squared minus 10x squared, 10x, sorry, minus 3x minus 30. And then we can simplify this. So we get 3x squared minus 13x minus 30, which hopefully is where we want it to be. It is, in fact, where we want it to be. And then because it's equals to 0, I can just swap these around. So I really don't need to worry too much because I can just say, well, if I swap them, I have to change all of the signs, but I can do that both sides. So 13 minus 3x, 3x squared minus 13x minus 30 equals to 0, which now looks exactly like what it needed to be. Okay, part B of this question then is write the roots of 3x squared minus 13x minus 30 equals to 0. So it's the exact same question. Yo, Steve, welcome in. It's the exact same expression as part A. So even if you can't show part A, you still have something to work with part B. So it would be really nice if the thing that we just had, we could just simplify back out, but we have to be a little bit more careful about it. Because we added in that extra 4x squared. So what I'm going to do is I'm going to divide each... Oh, I can't divide each of them by 3. Okay, I'm going to do it by hand, I think. So 30 factors of 30 are 30 and 1, 15 and 2, 10 and 3, 4 doesn't go into it, 6 and 5. And then so the reason that we do that is because when we're looking for an expression that is like ax plus b cx plus d. And the things in front of the a, or the a and the c here, are going to be are going to affect the first two terms, but this final term, this 30, is just going to be b times d, right? So we're looking for b and d that make up 30, and then that play with the others to get the other bits in the middle. So we can also make our lives easier by sort of saying that a will soak up whatever's complicated, so we're just looking for this expression. So I like the look of 6 and 5. I think those are probably going to be good. So we're looking for x, 5, and 6. So what have we got left? So we've got a and a c. So it might be the other way around. It might be that a is 1 and c is something. But if we expanded this out, we'd have acx plus 6a plus 5c x squared x and then 30. So we know that one of them needs to be negative, one of them needs to be positive, because we want this to be minus 30 here. And then we know that 6a plus 5c. So a times c is equals to 3, and 6a plus 5c is equals to negative 13. Okay, so let's play around with... I'm going to say that a is 3. So if a is 3, then this would be 6 times 3, which is 18, minus 5, which is 13. So we want minus there and plus there, and we want c to be 1 and a to be 3. Okay, so that gives us... We could solve this formally, these two equations formally, but just trying to try out different cases and see what works is also a valid option. So our brackets are 3x minus 5 and x plus 6 are equal to 0. And that's the reduced form of the expression up there, which means either one of these is equal to 0. So either x plus 6 is equals to 0 or 3x minus 5 is equals to 0. If the two things multiplied together is equal to 0, one or both of them are going to be equal to 0. So our solutions are x is minus 6 and x is 5 over 3, because those are values of x that give us those expressions equals to 0. Part 2 of that question, hence state which of the roots is not a solution of that expression, giving a reason. So I'm just going to nick the expression and put it over here so we can see it. Okay, so the reasons that something wouldn't be a root is because it doesn't fit into the domain of the thing. So what have we got? We've got log curves. So a logarithm is a function that looks like this. Okay. And it gets really, 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 really close to 0, but a log is never negative. And it can't, sorry, the log can never take in a negative value. So log of minus x is just like not possible. Like a circle edge, yeah. So that means that... Did I get that the right way around? Sorry, I got my signs the wrong way around up here. So that's plus and that's minus, because it would be minus 18 plus 5. Yeah, okay. Oh no, that's... Yeah, sorry. Minus, plus, minus, plus, minus, plus. Okay. Apologies. So basically, we can't have x be negative, and here we take just log of x. So x is minus 5 over 3 isn't... what was the question framing? Not a solution. So as log 2 of minus 5 over 3 is not real. Like there is some stuff that you can do there with logs of negative things, but for what we're considering, it's not real. So logs only take positive inputs of real numbers. Okay. Question 4. Coffee is poured into a cup. Good, that's generally where coffee should go most of the time. The temperature of the coffee, H degrees C, T minutes after being poured into the cup, is modeled by the equation H is AE to the minus BT plus 30, where A and B are constants. Okay, so we've got temp. And we've got time. initially, the temperature of the coffee was 85 degrees C. So H of T equals 0 is 85 degrees. State the value of A. Okay. Initially, the coffee was cooling at a rate of 7.5 degrees C per minute. Find the complete equation linking H and T, giving values of B to 3 decimal places. Cool. So, part A of this, so we have, as I say, H of T equals 0 is 85 degrees. And H, as a general expression, is AE to the minus BT plus 30. So we can just plug in the values and see what happens. So H of, as I say, 0 is AE to the minus B times 0 plus 30. So e to the power of anything, e is the graph that looks, as I said, it's the inverse of the logarithm. And it looks like this. Wrong arrow. Arrow there. Y, x, e to the power of x. So when it's negative, it's over here. When it's positive, it's over here. But e of 0 is 1. So this is a times 1 plus 30. So a plus 30. And we were told our initial time, our initial heat is 85. So we get a plus 30 equals to 85 degrees. So we just set the two conditions where h is equals to 0 here and here equals to the same thing. And then we can solve. So we get a is 85 minus 30, taking the 30 over to the other side. So 85 minus 30 is 55 degrees. 55. Okay. And then we get the information. Initially, the coffee was cooling at a rate of 7.5 degrees per minute. So we get when T equals 0, so initially, the rate the coffee was cooling, so the change in temperature over time was 7.5 degrees. Does E represent exponential, resultant, or vector? Sorry, I'm new to math. So in this case, E is the exponential. So that's this curve here. So exponential, exponential. Exponent. Basically, it's the inverse of the natural logarithm. So E itself is a number that's like 2.78 something, something, something. Let me check my calculator. I should know that better. 2.718, 281828, something, 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 and so on. Okay, so we have the rate in change in temperature at the start time is when T equals 0, dH dt, so that's the change in H over time, is 7.5. So our function, we can plug in our value for A, so we have 55 e to the minus bt plus 30. So we can take the derivative of this. In print, I like vectors to be Roman font, lowercase, and bold. When writing it, I underline my vector. Yeah, so I'm the same where, oh no, am I? When I'm handwriting it, underline for a vector, capital for a matrix. Yeah, bold, and then bold for a vector in font, but like writing it in bold gets complicated very quick. But we might have some vectors in this exam paper. I don't think so, though. This is mostly algebra. Okay, so coming back over here, we have this expression. So now we want to know what dH dt is. let alone what it is at 0. But dh dt is the derivative of this. So the exponent is weird, where d dx of e to the x is e to the x. The exponential function is one where the derivative is the same. So the rate of change of this graph at any point is the same as the value of the graph. And that's what we mean when we say things explode exponentially. And, you know, when we talk about degrees and not degrees, disease spread and things sort of growing out of control unboundedly, because, you know, the larger the value of x, the higher the value of x, the faster it's changing with respect to itself. Always at the arrows overline for vectors in writing. Yeah. There's no like right or wrong way of doing it, in my opinion. I like the underline. I think I was just taught it, so that's why that happens. Double underline matrices is a new one. I haven't seen that before, but that's cool. But yeah, so exponent is e to the x is e to the x. But when we have something in front of it, e to the, say, ax, then we sort of do the trick that we did before with normal powers, where that comes out the front. So that's ae to the ax. But we don't do anything different to that power now. This stays exactly the same. We're not subtracting one at all. We leave it alone. But what that means here is we get this as minus 55b. So we take down the minus b in front of the t, e to the minus bt. And then the plus 30, the derivative of a number is 0, so that just goes away. And then we were told that this is equals to, so dh dt evaluated at t equals 0. That's what that line means. It's just like I'm taking it at this point, which is minus 55b e to the 0 is equals to 7.5. So we can now just look at the second two here. So like this bit, and this bit, and try and solve that. So e to the 0 is 1. So I get minus 55b is equals to 7.5. So b is minus 7.5 over 55, which we were told to leave in a number of decimal places, 3 decimal places. 7.5 divided by 55 is 3 over 22 minus 3 over 22, which is minus 0.136 to 3 dp. It's actually 0.1 and then 36 recurring, but we got told to leave it to 3 significant figures. Did we have to... we had to find a complete equation. So I nearly left it there, and then we would have lost marks, because it's not just asking us to write down the value of b, it's also asking us to write down the complete equation. So h is equals to 55 e to the minus 0.136 t plus 30. And then that's the full equation. So curve C. Got a lot of differential equations to start off this exam paper. I feel like they really wanted to get you thinking about differential equations quite heavily. So we have a curve with a function y is f of x. The curve passes through the point P is 310 and has turning point at P. Given that the derivative of this function is 2x cubed minus 9x squared plus 5x plus k, where k is constant, show that k is 12. Hence, find the coordinates of the point C, of the point where C crosses the y-axis. So what the coordinates give us is that f of 3, so the input is equals to minus 10, and has a turning point at P, gives us that f, the derivative at P, is 0. What did I miss? You could represent exponential growth / decay for a number other than 2 point blah, 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 and find equivalent A and B, but E is the only number that has that property, so it's really convenient to work with. Yeah, basically, yeah. It is a good one. It's a weird number, but it's a good number. Okay, so, and then we've also been told that, so this thing is f prime of x, right? dy dx, f prime of x, all the same sort of thing. Show that k is 12. So part A, show that k is 12. We have that dy dx at x is 3 is equals to 0. So I think if we just plug in 3 for x, we should get out k is 12. So let's do that. So we get 2x cubed minus 9x squared plus 5x plus k evaluated at x is equals to 3 is 0. So let's try it. So that's 2 times 3 squared minus 9 times 3, 2 times 3 cubed minus 9 times 3 squared plus 5 times 3 plus k is equals to 0. So we need to be super careful about how making sure that we write down the right powers in the right places. So 3 cubed is 27. So not 3, yeah. So it's 2 times 27 minus 9 times 3 squared. So that's 9 times 9 plus 15 plus k is equals to 0. So 2 times 27 is 40 plus 14. So that's 54 minus 81 plus 15 plus k is equals to 0. 54 plus 15 is going to be 69. 69 minus 81 is equal, plus k is equals to 0. Okay, and then we have, I'm going to take it over, so we have k is 81 minus 69, and I'm just going to hope that that number is 12, which it is. So we have shown what we were required to show. And then part B was hence find the coordinates of the point where C crosses the y-axis. So sorry. So hence means like use the bit before. So the bit before k is 12 basically gives us that dy dx is equals to 2x cubed minus 9x squared plus 5x plus 12. That's the expression of dy dx. So needing to find where it crosses the y-axis means find, like our goal here is basically find full equation y equals f of x. So find out what f is and then plug in values where x equals 0, because that's where it crosses the y-axis, is where x is equals to 0. So to find y, we need to integrate dy dx. Okay, so integrating dy dx is integrating 2x cubed minus 9x squared plus 5x plus 12 with respect to x. And so when we differentiate, we take the power down and multiply it and then subtract 1 from the power. To integrate, so we have the integral of the integral of x to the n is x to the n plus 1 divided by n plus 1. So the order that you do them in is different as well. With differentiation, you take the power as was and do something with it. In integration, you do something to the power and then take it. So here, so 2x cubed goes to 2x, oops, goes to 2x to the 4, and then divide by the new power over 4, minus 9x cubed, divide by the new power, plus 5x squared, divide by the new power, and then we get plus 12x. And then because we are integrating without sort of limits, we need a constant of integration. So we get plus c, where c is some unknown number that we're going to solve for in a second. So I'm just going to take this over to the new page to have more space. Plonk. So if y is now equals to this. But we can't do anything with that because we don't know what the value of c is. But we know that we have the point 3, 310? 3 minus 10. Okay, so we can plug in values of x and y. I might tidy it up first, actually. So we get y is, so 2 and then 4. So that goes to, those cancel, and we are left with 2. 9 cancels, divide by it goes to 3. 5 over 2 is 5 over 2. So we get x to the power 4 over 2 minus 3x cubed plus 5 over 2 x squared plus 12x plus c. Not too tidy, but slightly better. And then plug in values of y. So we get minus 10. And then anyway, we have an x, we now have a 3. So 3 to the power of 4 over 2 minus 3 times 3 to the power of 3 plus 5 over 2, 3 squared plus 12 times 3 plus c. And this is where a calculator comes in handy. So we get minus 10, 3 to the power of 4 over 2 minus 3 to the power of 4 plus 5 over 2 times 3 squared plus 12 times 3 minus 10 is 18 plus c, so c is minus 28 by taking the 18 over. Okay, so then we have y is, the full equation is x to the power of 4 over 2 minus 3x to the power of 3 plus 5 over 2 x squared plus 12x minus 28. So when x is equals to 0, if we get rid of all of the terms that have x in them here, because they all go to 0, okay, all we're left with is the 28. So that's our remainder. So we get y is equals to minus 28. So it crosses the x-axis at 0. Crosses at 0, 28. And I think that was the end of that question. Yes. Okay, next. Relative to a fixed origin O, A is, okay, so now we're on to vectors. So what we were saying before kind of applies. So anywhere where there is a bold letter is a vector. And the way that we define I and j, we have our x value and we have our y value. So I is the vector here. Which is just one step in the x-axis. J is the vector here, which is 1 in the y-axis. So I and j are basically like how far along the x-axis and then how far along the y-axis you go. Okay, so we have relative to a fixed point origin, which is like the center. A is the point with position vector 12i. So that's 12 steps, 12 lots of that one vector in the x-axis. B is 16j. C is 50i plus 136j. Geez. D is the point with 22i, 24j. So I'm going to take that, shrink it, plonk it over there. So they're all positive, so I'm just going to leave myself space here. So we have 12i. Let's put it there. B is 16j. 50i, so like maybe 3 of those, and 136j, so that's going to be like up here somewhere. Actually, let's label these A, B, C, D. And D is 22, 24, so double and double. But C should be like, you know, all the way, like all the way off the page, really. It should be like all the way up here and really far away. Show the AD, so that's this line here, parallel to BC. Okay, well, that gives us some clue of where C should go. So I'm going to draw it parallel and then work backwards. So that's sort of what we're trying to get to, but we want to do it with equations, not just drawing it out and going C. So what we need to do here is find the equations of these lines, so AD and BC. So AD, and here now I'm using this vector notation with the arrow above to mean the vector from point A to B, for 2D even. Okay, and then the other thing to know is that two vectors parallel if vector A is some value times the other. So vectors have two things going for them. They have a size and they have a direction. So they're parallel if their direction is the same. And then the size is sort of the equivalent of like, if I have my vector here and I have my vector here, these two arrows are pointing in the same direction, but this longer one is a stretched out version, but the direction bit is the same. And that's why they're parallel. So what we're going to try and show is that AD as a vector is some value lambda of BC, or the other way around. So how do we do this? Well, great question. No. So a vector between 2 points, AD, is the same as saying the position vector of D minus A. Yes, because if I have a grid here, so I have my X and I have my Y, and I have my point A and my point D. Sorry, my capitalized letters for points. And my point D. Then this is like intro to vectors very fast. I do apologize. So the vector from the origin to A, okay, is our lowercase a. So that's our vector there. And then our vector from the origin to D is D. Okay, so those are the position vectors, right? So you go from the origin to the points. And then what we're saying is we want now the vector A to D. Tidy that up a bit. There we go. Okay, so we're looking for this vector here. Okay, from A to D. So that vector, the cool thing about vectors, in my opinion, I think it's quite nice, is that depending on your start and your end point, you can go sort of any route. okay? Because the shortest path is always going to be the same. So no matter which path I take, if my start and my end are the same of my vector, it gets me to the same value. So instead of going just straight along this green line, what I can do is I can go back along A to the origin, and then I can go up B. So I walk from this point here at A, I take minus A as a vector, and I take plus D. So that gives me that the distance from point A to point D is the same as going the distance from D minus the distance from A between the origin. So I'm sort of like completing the loop. As long as I start at A and end at D, it doesn't matter which way I go. I think that's everything we need. So we're gonna do it twice. We're gonna do it from A to D, and we're gonna do it from B to C, and then we're gonna see if they are some value multiple of each other. So we have that. Where is my black pen gone? There it is. All right, let's answer the question. AD is D minus A, which is, so D was the vector. I go all the way back up here to look at my answers. 22i plus 24j. Minus the value of A, which is 12i. Okay, so when we add and subtract vectors, we, in the same way that we do with other expressions, we add like terms. So we take all the i's together and we take all the j's together. So the i's, we have 22i minus 12i. So we have 20i. We have 10i even. It would help if I could actually do the maths bit. So we have 10i, and then there's no j term coming from the a bit, so we can leave the 24j alone. So that's our vector that takes us from A to the point D. Then we have BC, which same thing. So it's the second one. So point C minus point B. So this is now 50i. I really hope this works. Plus 136j minus, and then B was 16j. Same thing again. So we have 50i that we can leave alone because there's no I term coming from the second part. And then we just do the j's. So 136 minus 16 is 120j. Okay, so we now have these two terms. So if I divide by 5 with B, I get 5. So I get my 10i, and then 120 divided by 5 is, in fact, 24. We get 5 lots of AD. So they are, in fact, parallel because one is just a scalar multiple of the other. Next bit. Ooh. Thank you for the follow. Welcome, welcome. Okay, so part 2 of this question then has, so we have the AD is parallel to BC. We have that points A, B, C, D are used to model vertices, so the sides of a running track in the shape of a quadrilateral. One lap is all 4 sides. Lengths of sides are measured in meters. Sorry, did an American. Meters. Given a runner takes 5 minutes for 2 laps. Calculate average speed. Average speed in kilometers an hour. Okay, so immediate first thing to note here is that the question has immediately asked for kilometers an hour. But they've given us time in minutes and the distance in meters. So we're going to have to do some translation between meters per minute and kilometers per hour, especially because distance over time is meters per second. So we're going to have to be a bit careful around that. But we should be okay. So we want the average speed. So average speed is total distance over the total time. So let's work this out in kilometers an hour. So the total time is 5 minutes, which is 5 divided by 60 hours. Okay, not too bad so far. Total distance, so it's 5 minutes for 2 laps. And the gut reaction there might be to do just half the time, but we need to stick with what we've been given. Okay, so total distance is going to be equals to 2 lots of the distance for all 4 sides. You were speed. Oh, you weren't speeding. Well, I'm sorry. That is unfortunate then. So we have like our parallelogram, maybe not a parallelogram, but our quadrilateral here. A, B, C, D. So we need the size of AB plus the size of BC plus the size of CD plus the size of DA. Okay, so we need all 4 sides. We have from before AD was from our previous answer, so we can nick that one. So that was 10 plus 24J. And we had that BC was 5 lots of AD. So then what we're left with is AB, which is... So vector from A to B is the vector B minus the vector A. And I have up on the side, because I really can't bother to scroll in this thing anymore. So B was 16J minus 12I. And then we can't do any simplification of that because they are very different. Okay, and then the only other one we're missing, so we've got AB, we've got BC, we've got CD. CD is the last one. So that's D minus C. So D was 22I plus 24J. And C was minus even 50I plus 136J. So if I do this, 22 minus 50 is 27. 28, I can do maths, minus 28I, minus 24 minus 136 is going to be 112J. Okay, so we have all of our vectors, but what we said was we wanted the distances. And the thing to know here, I've got DA because, you know, you go, say, round the track in this direction. DA as a vector is going to be negative AD. But it's not going to matter too much because when we're talking about length, so what we want here, what I've done this notation with the vertical lines, is the length of the vector. And the length, the distance doesn't change, but the direction is the thing that goes opposites. So to find the distance of a vector, what we do is we take all of the components and we square them, we sum them, and then we square root them. So this would be, so 10 squared plus 24 squared, square rooted. And that might look vaguely similar. If you remember one thing from school maths, it might be perhaps this thing. Okay, so Pythagorean's Pythagorean theorem says that your hypotenuse, so the longer side of a right angle triangle, is the same squared as the sum of the other two sides squared. And this is what we do when we talk about length of vectors, because if you remember that the way that we write these vectors is, 10i plus 24j, the resultant vector is, if I plonk those two things together, is actually, so I do one and then I do the other, I end up with this line here. Yeah, this is also 24j, so 10, 24. This is the total vector AD. Thought it was going to be SOHCAHTOA. Do you think SOHCAHTOA is more memorable than a squared plus b squared equals c squared? I'd be curious to know from outside of, outside of the maths world, which one people remember more from school. Unless it's something else, if there's something else that's like super memorable. But because I and j, because they align with the x and y axes, they are perpendicular to each other. So they're at a right angle. So they always make a 90-degree right angle with each other. So we can always use Pythagoras to find them. So we take the square of the I term, and then we take the square of the j term, add them, and then we square root, and that gives us our length. So here, this is going to be some number. Another hour of algebra. Oh my god, she really is doing maths. It's terrible. So this is going to be 100 plus 24 squared. Square rooted is, 26. Nice. BC is going to be, so I can just take, okay, I can cheat here a little bit where I know that it's 5 times the vector. So I could do it properly, and I could do 5 squared, 10 squared, plus 5 squared, 24 squared. I can take out a 5 squared. 24 squared. But basically I can just do 26 times 5, and that gives me my 130. Then CD is going to be square root. So even though they're minuses, because we square them, we don't have to worry about them. But technically, yeah, it's 28 squared, minus 28 squared plus minus 112 squared. But the squareds do wonderful things and get rid of them. And that gives us a less than nice number, I think. 28 squared plus 112 squared. No, 112 squared. 28 square root 17. And then finally, AD, BC, CD, AB is the square root of 16 squared plus 12 squared. Watch out! Which is 20. Okay, so 1 lap is going to be equals to 26 plus 20 plus 130 plus 28 root 17 meters. Okay, meters. So So 176 plus 28 root 17 meters. So what we need to do is our total distance, remember they did 2 laps, is 2 lots of 176 plus 28 root 17. So that's in meters. So we need to divide by 1,000 to get kilometers. Oh, okay, I'm just going to plug all of that into a calculator. 176 plus 28 root 17 over 1,000 is 0.58 kilometers. So our average speed, because if you remember way back when, our average speed is our distance over time. So that's that thing over 5/60. Which is approximately equals to 6.99 kilometers an hour. Ooh. And are they all right with, did they say how many to leave it in? No, they didn't say, but that's to 2 decimal places or 3 significant figures. In this question, you must show all stages of your working. Solutions relying on calculator technology are not acceptable. So basically what this is saying is like, because calculators got so good that they can do this for you. The point is not calculators. Implicit differentiation time? I think it is. I think it must be. So we have a curve with an equation. Find dy dx in terms of x and y. So we want to find the gradient of this curve. Lux, why is a printer lying to you? What is happening? Okay, find the point P is -2,5 lies on the curve. So that's going to give us a nice way to figure out some coefficients going on here. We have this expression, find dy dx. So the way that we're going to do this is we're going to differentiate the entire thing. And we're just going to differentiate it like normal. But there's a few things that we need to know. So we've got this term is nice and normal. We're happy with that. This term has an x and a y in it. So when you differentiate things that have 2 functions in them, so we have f of x, g of x. If we want to differentiate this, I'm just going to do it this way actually, d dx. We need to use what's called the product rule. And that basically says that we differentiate one and we leave the other alone. And then we differentiate the other, leave the other alone. So this is going to be f prime of x, g of x, plus f of x, g prime of x. And this is the product rule. Okay. And the other thing to know is that d dx of y is dy dx. So dy dx is dy dx. Feels a bit overcomplicated, but it will come in useful. So when we differentiate something as y, so like this term, for example, we're going to differentiate it as if it was a normal function, but then multiply that by y of x. And this is like technically chain rule, but not explicitly. Chain rule as we learn it is something a bit different, but what's happening there is the chain rule because y is a function of x. So we have to do something in there. Product rule rules, quotient rule rules. I so agree. You don't need the quotient rule. Just one of the things in the product is 1 over. So we'll do it bit by bit. There's like 6 different things in a trench coat happening here. So I will try and do it bit by bit. So we start off with x cubed plus 2xy plus 3y squared is equals to 47. Okay? Nice and easy. Starting with x cubed. X cubed, there's no y's going on. It's the thing that we saw before. So we take the power, we multiply by the power, and then we subtract 1 to it. So this becomes 3x squared, right? Done. Leave that alone. This thing then, we need to treat the 2x and the y as two different functions and then use the product rule. So differentiating 2x gives us 2. So take 1 away from the power. Sorry, take 1 away from the power and leave the rest alone. And then we leave the y alone. We leave the second function alone. Plus, we leave the 2x alone. And then with the y goes to dy dx. So that is that bit. The 3y squared, we're going to have a dy dx because we're integrating, we're differentiating a function of y now. So we need to multiply by dy dx. And then we treat this as if it was normal. We treat it as if it was an x. So 3x squared, we take the power of 2 down. So if this was 3x squared, it would go to 6x. Okay, so the power of 2 comes down, multiply out, power 2 goes to power of 1. So because that goes to that, this then becomes 6y. And then the 47 is a constant, and constants differentiated go to 0. So all in all, this equation becomes 3x squared plus 2y plus 2x dy dx plus 6y dy dx is equals to 0. And the gut reaction there is to say, well, we're done, but we're not, because what we've been asked to find is dy dx in terms of x and y. So we're trying to get to dy dx equals some stuff, and we're not at that yet. So instead, what we need to do is start grouping terms. So these bits don't have dy dx in them, so we can take them over to the other side. So I know that I'm going to have some stuff equals to minus 3x squared plus 2y. Take those over, need to make what was positive negative. And then on the rest of the terms, they've both got a dy dx, so we can factor that out. So factoring it out from the first expression gives us 2x, and factoring it out from the second expression gives us 6y. Final thing we need to do then is divide by that 2x plus 6y. So we have dy dx is minus 3x squared plus 2y over 2x plus 6y. So that is our expression for dy dx. That's part A. Point P is that lies on this curve. Find the equation of the normal to the curve at P, giving your answer in the form ax plus by plus c equals 0, where a, b, and c are integers to be found. Okay. Some things to know. So we have a curve C. That's our curve. We have our point P on the curve. The equation, put that in a terrible place, P. There we go. The equation to the normal is normally computed. Get it? Normally. Negative reciprocal. Yeah, exactly. So it is the perpendicular to the tangent. So the tangent of this curve is the one that touches it exactly once and has the same gradient. So the dy dx is the same. So this is our tangent. Because at this curve, it touches it just there, and it has the same dy dx. The equation of this line has the same gradient there. The normal is perpendicular to that. So the normal will be the point that has let that load. So our normal is 90 degrees away from our tangent, which means that its gradient if this has a gradient, tan is the same as dy dx of p, of this function, then the normal, so the gradient of the normal is minus 1 over tan. Yeah, so negative reciprocal in this case. Reciprocal means 1 over negative, subtract it. So what do we need? We need, this is then minus 1 over dy dx at p. We need to figure that out. So let's first find dy dx at p, and then we find the equation of the normal. Okay, so we have, this is our equation dy dx. So I'm going to nick this and bring it over to the other page. And then our point P was minus 2, 5. dy dx evaluated when x is minus 2 and y is equals to 5. So we just plug in values of x and y here. So wherever we see an x, we plug in a minus 2, and wherever we see a y, we plug in a 5. So we should get minus 3 times minus 2 squared plus 2 times 5 over 2 times 2 plus 6 times 5. So 3 times 4 plus 2 times 5, so 10. So we get 22. So minus 22 over 4 plus 30. That feels like it divides. Is that? Oh, minus 2. So that is minus 11 over 13 is the gradient of, yeah, thank you. So minus 2, sorry, the gradient of this point, of the curve at this point is minus 11 over 13. So m of normal is 13 over 11. Okay, so we've been told to find in the form ax plus by plus c equals to 0. So we know that the normal is a line that passes through the point P, right? Because it's the normal at that point. It does pass through the point P. So we know that minus 2, 5 sits on this thing. And we know that the gradient is 13 over 11. So I should draw it going positive, but, you know, oh well. So that should be enough information to figure out what we need to do. Because the equation of a curve is y minus y naught is equals to mx minus x naught. So that's our equation of our line. So if we plug these in, where y naught is the values of p, it's a value of a point on the curve. So y minus 5 is equals to 13 over 11 of x minus minus 2. So the minus and the minus cancel out and become a plus, which is nice. Okay, so, and then we just need to expand this out because we want it in the form ax plus by plus c equals 0. So we have, I'll do it this way. So 11y minus 55 is 13x plus 26. And then we want everything on the same side. So we're going to do right-hand side, but bring it over. So 13x minus 11y plus 26 plus 55 is equals to 0. So that changed sign and that changed sign. Yep. So we should be left with 13x minus 11y, 26 plus 55 plus 81 is equals to 0. So that's our equation of a curve in the form requested. Ooh. That was a hard question. For how many marks was that? Okay, 7. Right. We've got some values. We've got some trig going on here. Oh, no, we've got an almost trig. We've got series as well. How exciting. Okay. Express 2 cos theta plus 8 sine theta in the form r cos theta minus alpha, where r and alpha are constants. R is greater than 0 and alpha is between minus 0 and pi over 2 even. Give the exact value r and give the exact value of alpha in radians to 3 decimal places. So basically what we're going to do is we're going to write both sides and then see what needs to happen. So part A, what was it? 2 cos alpha plus 8 sine alpha is equals to r cos theta, sorry, 2 cos theta plus 8 sine theta, theta minus alpha. So this is going to be a look it up and check type of thing, where what we want is something in terms of cos theta and something in terms of sine theta. So, double angle formula here. This is where the formula book comes in handy. Where is it gone? Double angle. Right. So cos of, we've got here a minus b. I'm just going to write it out actually in its general form. Cos of a minus b is the same as cos a cos b minus sine. Nope, flip the signs. Plus sine a sine b. Okay, so this is something that was given, so I don't have to worry too much about checking it. But as soon as I see two angles inside of the same thing, inside of one trig function, I can check my trig identities, and this is always true, right? I should technically write it like that. Do it properly. So it's an identity. It's always true for values of a and b. So we can plug in alpha and theta, and we get that this expression coming back here is r cos theta cos alpha plus, make sure the r goes across, sine theta sine alpha. Now we want to play a game with it where the coefficients need to match. So here we had 2 cos alpha theta plus 8 sine theta. Please read what I'm writing rather than what I'm saying. I'm struggling here. But we have cos theta multiplied by 2. And that means that r cos alpha must match up, right? There's no other cos thetas happening here. So the coefficient on one side is the same as the coefficient on the other. And then similarly, we've got an 8 here, and that's going to match up with these two here. So we have 8 is equals to r sine alpha, and 2 is equals to r cos alpha. So that's just by comparing coefficients. That's the technical maths term for it, is we compared coefficients. So what can we do with this? Well, there's another identity that we can use to try and get rid of it. To try and find, because we want to find r and alpha. That's the point of this, is find r, find alpha. So if we have sines and coses, we can use that sine squared of alpha plus cos squared of alpha is always equals to 1. Right? When we square our trig functions sine and cos and we sum them, they equal to 1, always. Which is quite useful. So if we do that, if we square both of these and then add them, then what we'd get is 8 squared plus 2 squared is equals to r squared sine squared alpha plus r squared cos squared alpha. And here, like sine squared alpha is sine alpha all squared. It's just we write it on the function, because if I wrote sine alpha squared, it kind of looks like I've squared the alpha, not the whole thing. So we bring it in front of the thing that the sine is acting on as an operator. So we have 8 squared plus 2 squared is, I can pull out an r squared from the front. Sine squared alpha, but cos squared alpha, which is what I said was 1. So that disappears. So if I want r, I just take the square root of the other side. Again, looking very similar to Pythag, which is not without a point. It is. It's all Pythagoras, basically. He really won the lottery on putting his name on the most used thing, I'd say. So r is equals to 8 squared, which is 64 plus 4, so square root of 68, which is 2 root 17. This paper really likes root 17. I'll give it to them. So we'll leave that alone for the minute. And then we need alpha. So what we can do with that is if we go back to our 2 equations here, our 8 is r squared sine alpha, and our 2 r cos alpha. We only want one. We want something with alpha equals to something. So we could solve one of these, but there's a quicker way we can do it. And that is by using that sine of alpha over cos of alpha is equals to the tangent of alpha. So we can introduce a third trig function to just get one equation. So if we do that, if we divide these 2 equations by each other, we get sine of alpha over cos of alpha. And technically we get r sine alpha over r cos alpha, but the r's disappear, is 8 over 2. As I say, the r's disappear. So we get tan of alpha is 8 over 2. And then we need the inverse tangent. So tan, if I do it underneath. So we sort of undo that tan function on that side. So we get inverse tan of 8 over 2, which if I take inverse tan of 8 over 2, and I make sure that I'm in radians because it said we were in radians. 1 point, and it told me to do it in 3 decimal places. 3 to 6 rad to 3 dp. So our expression, just to write it all out, so 2 cos theta plus 8 sine theta is 2 root 17 cos theta minus 1.326. And that's our solution, okay? Then we have part B of this question, which seems unrelated. Gonna be honest. First 3 terms of an arithmetic sequence are cos x plus sine x, cos x plus 2 sine x. X is not equal to n pi. Given that S9 represents the sum of the first 9 terms in the sequence as x varies, find the exact maximum value of S9. Then deduce the smallest positive value of x at which this maximum x9 occurs. So this is, again, we're going to jump back to our formula booklet. And somewhere in here, there's going to be series. Have I gone past it? There is. Okay. So from the formula book, we have the arithmetic sequence. Arithmetic series, we have the S of n is 1 over 2 na plus L, or 1 over 2 n 2a plus n minus 1 d. I love it when I mix brackets. There we go. So here, the n is the term it is. the A is sort of your starting point. And then D is what's being added. So in the expression before, we had x, cos x, so this is our A. And then each time it's adding sine of x. Okay. So our D here is sine of x. So A is cos x, D is sine x. So S9 is going to be 1 over 2, 9, 2 cos x plus 9 minus 1 sine x. Ah, I see why they're related now. So this is our equation for our sum of this series. So we have 4.5 out the front, 2 cos x plus 8 sine x, which was precisely the thing that we had in the start of this is precisely the thing we had in this part, right? Like the start of this expression, express 2 cos theta plus 8 sine theta. So we've already got, we can rewrite it in this way. So let's have a look at what happens if we do that, because we're looking for the maximum value this can take, okay? So we get 4.5 times, and we know that this is 2 root 17 cos x minus 1.36. So 326 even. So what we're looking for is max of x9. So this is going to be maximum when cos of this thing is equals to 1. Okay? And that is because cos is the function that looks like this, which has a maximum value at 1 and a minimum value at -1, right? It never outputs values bigger or smaller than 1 or -1. So because this is the cos term multiplied by something positive, the something positive is fixed, and the only thing that's changing is this expression here. So this is biggest when it's equal to 1. It's always going to be smaller than 1. So if this is equals to 1, then the maximum value S9 can have is equals to 4.5 times 2 root 17, which is 9 root 17. Was there a part 2 to that bit? Find the exact maximum value of S9. Done. Deduce the smallest positive value of x at which this maximum value of S9 occurs. Okay. So smallest positive value of x for which it occurs. So it happens at x is equals to 0, and it happens for whatever value of x happens when we're over here as well. Also get a half enjoy your maths kids. See you Monday. See you Monday. So we're looking for when cos of x minus 1.326 is equals to 1, which happens whenever, so the inverse cos of 1 is equals to 0. So that happens when x minus 326 is equals to 0, right? Because it happens here, and that's going to be the smallest value that we can take, is this whole curve along here is our like x minus 1.36. So its x is exactly 1.326 to 3 decimal places. That's the smallest value of x that has that. It does repeat, so it would also happen at 2 pi plus 1.326 and 4 pi 1.326. But yeah, that's the smallest value of x that we can take. So if you enjoyed this, I am hoping to be back every Friday afternoon with more math streams. I also do co-working streams Mondays and Tuesdays, starting in the morning, going for most of the day. Have a wonderful rest of your day, week, month, year, however long it is until I see you again. I hope you come back. I hope to see you again sometime. Look after yourselves. Hwyl fawr. Bye-bye.